All right, in this video we're going to take another look at numerical limits. And in this case what we're going to be doing is calculating the limit of the floor function. The floor function might not be a function that you are experienced with. So let's just take a look at it. I'm going to again use Desmos to take a look at the limit. So the floor function, I just have already typed it in here. And if you look at the graph of the floor function, that's what it looks like. So it's a piecewise function here, and so it has, if you tried to write out the formula with all these little steps here, be rather complicated. So they just use the floor as the title for it here in Desmos. So what does the floor function do? Well, for whole numbers, 4, 5, oops. Set up. 4, 5, -7. You can see that it just spits out the number that you typed in, basically. For positive numbers, like if I have a number like this, 2.764. So for positive numbers, what the floor function does, it just basically chops off this decimal, the part after the decimal right here. So if I had 5.763, right, it would just chop this part off right here and give you a 5 as the output. If I had 0.763, again, it would just chop this off and give you that 0 right there. For negative numbers, it's a little bit different. It doesn't really correspond to chopping off those decimals anymore, but it goes to the next, the integer that's less than this, but the biggest one that's that. And in this case, it's 2. So, but in this example, we're taking the limit as x goes to 2 of the floor function, and so. Let's just go to the tables again, just like we have been doing. So, oops, this was the limit as x, nope, sorry. 2 is where we're taking the limit here. So I'm going to need to change those to this and not negative. All right. So these numbers are getting closer and closer to 2. The x values, right, are getting closer and closer to 2. And here are the corresponding y values, or output, or f of x values, however you want to think about them. And you can see that the output is pretty clear what's going on here. I'm just getting exactly 2 each time. So that's what's going on to the right of 2. And then here I need to just totally change these to look at the other side. So 1.9, 1.99, 1.999, and you can see what's going on here also. Pretty clear that as we get closer, as these x values get closer and closer to 2, then the corresponding y values get closer and closer to 1. In fact, they're identically equal to 1, right, in each case, because the floor function is just basically chopping off the 0.9s right here. So what to make of these results? We can see that from the right, on the right-hand side, the y values are getting closer and closer to 2. Whereas if we stick with numbers on the left, the y values are getting closer and closer to 1. So in this case, the same thing is not happening on the right side as what's happening on the left side, like all of the other examples that we did. So in order for you to say that the limit is equal to some number, right, what must happen here is that the behavior on the right must be exactly the same as the behavior on the left. And we can see that that's not happening here. So in this case, the limit does not exist. We cannot say that the y values get closer and closer to one single specific number the closer the x values get to 2 in this case, because we can't say that it's 2, right? Because if we stick with these x values, then those numbers are getting closer and closer to 1. They're not getting closer and closer to 2. We can't say that the limit is 1, right? Because if we stick with these x values, hey, they're getting closer and closer to 2, but their y values are getting closer and closer to 2 also, not to 1. So the limit's not 2, it's not 1. In this case, there is no one single value that we can say is the limit. So going back to the original problem, the only conclusion that we can make right here is that the limit as x goes to 2 of the floor function does not exist. That's the best that we can say.